Thank you, Chairperson. I'm Ryu Miwa. I'd like to talk about transaction processing using a high-performance proxy in distributed KVS. Our method transparently provides transaction processing functions to distributed KVS by performing exclusive control and transaction processing on the proxy.
Databases must handle the large volume of data and number of requests with the development of IoT and big data. To handle these things, distributed key-value stores are widely used. D-KVS manages a single data structure of key-value pairs and distributes data to multiple database nodes. However, D-KVS needs distributed consensus protocols for exclusive control when performing transaction processing in the distributed environment. So, efficient exclusive control is difficult because a lot of communications occurs by distributed consensus protocols. To address this problem, we propose a transparent transaction processing method by a high-performance proxy without depending on distributed consensus protocols and special hardware devices. In our method, we provide ACID-compliant transaction processing functions to D-KVS by performing exclusive control and transaction processing on the proxy. We eliminate the distributed consensus protocols for exclusive control on the proxy. Also, since we only install the proxy, special hardware devices are not required. D-KVS has a problem with exclusive control. P2P type D-KVS assumes eventual consistency because all KVS nodes accept requests from clients. However, transaction processing requires a strong data consistency. We consider the case where two clients make atomic writes to the same key. First, client 1 sends an atomic write query to any KVS node. The KVS node that receives the query routes the query to the responsible node. At the same time, we consider the case where two clients 2 also write atomically to key 1. In this case, multiple clients may write atomically to the same key, so KVS nodes must choose a consistent state across the responsible nodes. D-KVS uses distributed consensus protocols such as Paxos to communicate between the coordinator and the responsible node and select a consistent state of data. However, Paxos requires at least 2 round-trip communication between the coordinator and the responsible node. So, communication cost for exclusive control increases. NewSQL provides transaction processing functions in the distributed environment. NewSQL has the scalability and availability of NoSQL and the transaction processing functions equivalent to RDB. Typical examples are Google Spanner and CockroachDB. Spanner manages the order of transactions by adding timestamps to the transactions and ensures data consistency even in the distributed environment. In the conventional method, the lock is released as soon as write 1 is executed. If write 2 is executed at the same time as unlocking, write 2 with a timestamp earlier than write 1 will be committed later due to the time difference between the nodes. In Spanner, when write 1 is executed, the lock is released after waiting for a time longer than the time difference between the nodes. Then, write 2 is executed. In this way, Spanner intentionally waits for more than the time difference between nodes to ensure that they are committed in order. However, a high-precision atomic clock is required to reduce this waiting time. A high-precision atomic clock has a deviation of 1 second every 30 million years. Introducing special hardware devices complicates operation management and drastic system changes. We proposed a query aggregation method using a proxy. We introduced the proxy to the D-KVS for the aggregation and improved the performance of D-KVS. In this method, client requests queries to only the proxy. The proxy collects the same distinct queries and aggregates them into single packets. Then, the aggregated query packets are directly sent to the data nodes. Packet processing can be accelerated by using DPDK. DPDK is fast packet processing framework developed by Intel. DPDK is polling packet arrival, which decreases the interruption overhead, and packets are bypassing the kernel, which decreasing context switches. These features enable the fast packet processing. SquareDB is one of the D-KVS. It is compatible with Cassandra. SquareDB uses a fast user space network stack based on DPDK. It achieved 10 times higher throughput than that of Cassandra. Therefore, using DPDK improves the performance of the proxy.
Throughput of D-KVS improved by query aggregation by the proxy and packet processing speed up by DPDK.
Therefore, we introduced a high-performance proxy in D-KVS to transparently provide transaction processing functions without using special hardware devices. The distributed consensus protocol is eliminated by performing exclusive control on the proxy. Also, we provide transaction processing functions to D-KVS by performing transaction processing on the proxy. The proxy is implemented using DPDK and query aggregation. The proxy runs on many core CPU machines, and the cores are assigned to each data node. Now, 64 cores and 128 threads of CPU is available. So, single proxy can handle a few dozen data nodes, and single proxy can achieve a few gigabit per sec throughput. The distributed consensus protocol is eliminated by performing exclusive control on the proxy. When performing exclusive control on D-KVS in the conventional method, there is a problem that the communication cost required for exclusive control is high because distributed consensus protocols are required between the nodes. However, the proposed method eliminates the distributed consensus protocol by performing exclusive control on the proxy and reduces its communication cost. We implemented new queries that are begin, commit, and rollback to realize transaction processing. The begin query initiates the transaction processing. The commit query applies transaction processing. The rollback query discards transaction processing. Multiple threads run inside the proxy to take advantage of many cores. Routing threads calculate the hash value from the query key and route the query to the transaction thread. Therefore, queries with the same key will be routed to the same transaction thread. Transaction threads perform exclusive control by lock and transaction processing, then send queries to D-KVS. Each transaction thread has log management that manages logs for exclusive control and transaction management that manages transactions. Log management has a client state table and a log management table. Client 1 initiates a transaction. The client state table remembers that client 1 becomes a transaction start state. Next, transaction management creates an in ProxyDB to execute the query during the transaction and reserves a query storage area to hold the query during the transaction. Client 1 sends write queries and read queries to the proxy. The proxy gets locked by the key of the query and the lock information is registered in the log management table. Transaction management executes the queries in ProxyDB. Therefore, the client can successfully read the value updated during the transaction from the in ProxyDB. In addition, transaction management retains write queries during the transaction in the query storage area. Finally, the client sends a commit query to the proxy. Lock management removes client 1 information from the client state table. Transaction management retrieves the queries from the query storage area and sends them to D-KVS. Transactional write queries are executed in D-KVS and the values are persisted. The proxy deletes the in ProxyDB and query storage area and unlocks keys if the commit is successful. If another client initiates a transaction, transaction management creates in ProxyDB and reserves query storage area for each transaction. Therefore, the proxy can process transactions in parallel. Transaction processing in the proxy achieves ACID properties. Achieve atomicity by commit and rollback. Achieve consistency and isolation by exclusive control by lock and processing queries with the same key by the same transaction thread. Achieve by persisting the transaction processing results with D-KVS. So, the proxy provides ACID-compliant transaction processing functions. The proxy transparently provides transaction processing functions. Clients can use transaction processing functions by using begin, commit, and rollback queries without being aware of the proxy because the proxy supports D-KVS protocol. We made 3 evaluations. First, we evaluated the proxy overhead using YCSB to confirm the overhead by introducing the proxy that implements transaction processing function. Second, we evaluated the performance of lightweight transactions to confirm the effectiveness of exclusive control by the proxy. Finally, we evaluated the performance of transaction processing to confirm that transaction processing performance is faster than new SQL. The evaluation environment is like this. We evaluated using a 10 gigabit per sec network. We evaluated the proxy overhead using YCSB. YCSB offers 6 different workloads, but excludes workload E that the proxy does not support. The YCSB client ran 160 threads, and we used 10 Cassandra nodes for the KVS nodes. This figure shows the throughput of each method. The vertical axis represents throughput, and the horizontal axis represents each workload. The blue bars represent Cassandra, and the yellow bars represent proposed method. The result was lower than Cassandra throughput for all workloads. Workload F, which has the smallest difference, has a 0.2% decrease, and workload B, which has the largest difference, has a 12% decrease. This means that the proxy that implemented transaction processing functions overhead is small. We evaluated the performance of lightweight transactions. Lightweight transactions is a transaction function provided by Cassandra. Lightweight transactions uses the distributed consensus protocols to atomically update records that meet the conditions. We created a benchmark of executing 1 million lightweight transactions and measured each execution time, then calculated the median. We used up to 10 Cassandra nodes. This figure shows the median execution time, when write-write transactions are executed 1 million times. The vertical axis represents execution time, and the horizontal axis represents the number of clusters of Cassandra. The blue bars represent Cassandra, and the yellow bars represent proposed method. In the proposed method, the execution time of write-write transactions was reduced by 6% when there was one Cassandra node, and the execution time was reduced by 39% when there were 10 Cassandra nodes. This is because the communication cost by the distributed consensus protocol could be reduced by performing exclusive control on the proxy. So, we confirmed that the effectiveness of exclusive control by the proposed method. Finally, we evaluated the performance of transaction processing. We created a benchmark that runs 1,000 transactions with 10 inserts, and we used 10 Cassandra nodes and 10 CockroachDB nodes. We evaluated the performance when transaction processing is performed by the proposed method and when transaction processing is performed by CockroachDB. This figure is a histogram that shows the frequency of transaction execution times. The vertical axis represents frequency, and the horizontal axis represents the execution time of transactions. The blue bars represent CockroachDB, and the yellow bars represent proposed method. This table shows the average, median, maximum, and minimum values for each evaluation. The evaluation result shows that the proposed method can process transactions faster than CockroachDB. This is because the communication cost by the distributed consensus protocol could be reduced by performing exclusive control on the proxy. However, there are many functional differences in transaction processing between the proposed method and CockroachDB. The proxy supports begin, commit, and rollback statements. CockroachDB provides transactional features other than begin, commit, and rollback as shown in the table. In addition, CockroachDB has the ability to automatically retry transactions and resolve resource contention required by transactions. Therefore, we consider that the difference in transaction execution time between the proposed method and CockroachDB is due to their functional difference. I will conclude my presentation. We propose a transparent transaction processing method without special hardware devices. The proxy eliminated the distributed consensus protocols by performing exclusive control and transaction processing and provided transaction processing functions to D-KVS. We confirmed the effectiveness of the proposed method while ensuring its performance by performing transaction processing with a high-performance proxy. As a future work, we will implement additional transaction functions. Also, we will eliminate single points of failure. Thank you for your listening.